This video is an example of analyzing a circuit that's a network of capacitors. So I've gone ahead and drawn my circuit here. There's a battery with an EMF of 18 volts. Up at the top here is capacitor C1. It has a capacitance of 240 microfarads. And then there are two capacitors in parallel. In the middle is C2. Its capacitance is 130 microfarads. And on the end is C3. It has a capacitance of 590 microfarads. So just to pause and think about what we know conceptually about circuits, capacitors C2 and C3 must have the same voltage across them because they are connected in parallel. So whatever voltage is on this top bit of wire is shared by both capacitors, and whatever voltage is on this bottom wire is also shared by the two capacitors. So they have the same potential difference across them. The charge across C1 is equal to the sum of the charges on C2 and C3. That's because of conservation of charge. So if there are 10 coulombs of charge on this plate, that must leave behind negative 10 coulombs of charge, but shared, because of this junction, shared between C2 and C3. So I am going to reduce this circuit to a simpler circuit using equivalent capacitance. A tip for creating equivalent capacitance is to begin sort of at the far end of the circuit. These two capacitors are in parallel, so I will find a equivalent capacitance that replaces these two. The way this would work in building an actual circuit is you could take out these two capacitors in parallel and replace them with a single capacitor with the equivalent capacitor value, and the circuit would work just the same as it works right now. So I'm going to redraw the circuit with that single capacitor that replaces only C2 and C3. I can't replace all three at once because C1 is in series with both C2 and C3, but C2 and C3 are in parallel. It's a mixture of rules. I can't mix series and parallel additions to create a single equivalent capacitance quickly. So I'm going to do it sort of one step at a time. So I've redrawn my first step of my reduced circuit, and I'm going to combine C2 and C3. They are in parallel. For capacitors, we just add them when they're in parallel, and so these have a capacitance of 720 microfarads. Next, I'm going to combine C1 with this equivalent capacitor I just found that replaced 2 and 3, and that will now create a circuit with a single equivalent capacitor. So here's my circuit for the single equivalent capacitor. For combining capacitors in series, they're added using the inverse equation. So you might want to pause the video and do that calculation, see what you get. I get 180 microfarads here. So now we're ready to start to calculate the values of these capacitors, charge and voltage across the capacitors. So to begin with, the charge across this equivalent capacitor is going to be the same as the charge on C1. It would be the same as the charge on this equivalent capacitor here, C23, but that's going to turn out to be not useful. So I will use the voltage and the equivalent capacitor, C equivalent of 1, 2, and 3, to calculate Q on this capacitor, which is the same as Q1. So Q1 is equal to the equivalent capacitor's capacitance times the EMF of the battery You might want to calculate that for yourself. Pause the video and then you can check it. I get that Q1 equals, I'm going to keep some extra sig figs here, 0.00324 coulombs. When you use the capacitance, don't forget that micro is 10 to the minus 6. So once I have the charge on capacitor 1, I can now use that charge and the capacitance of capacitor 1 to calculate the potential difference across just capacitor 1. So the potential difference across capacitor 1 is the charge on capacitor 1, Q1, divided by the capacitance, 240 microfarads. So go ahead and calculate that. I get that the potential difference across this capacitor, should be 13.5 volts. Again, I am keeping some extra sig figs here, partly because I want to check my answers at the end, and it'll come out better if I keep the sig figs. So once I know the potential difference across capacitor 1, I can calculate the potential difference across the equivalent capacitor for 2 and 3, which is the same as the potential difference across each one of C2 and C3 because they have the same potential difference, which is the same as the potential difference across their combined equivalent capacitance. We can do this using Kirchhoff's loop law. So there's a total of 18 volts across both capacitors. If V1 takes 13.5 of it, we just have to figure out what's left over for V2 and V3. So that would be 4.5 volts, because 4.5 volts plus 13.5 volts equals the total 18 volts that the battery is putting across the circuit. Now that I know the voltage drop across each of these capacitors, I can calculate the charge on each one of those capacitors. So the charge on capacitor 3 is equal to the capacitance of capacitor 3, 590 microfarads, times the voltage on it, 4.5 volts. And when I multiply those together, I get 0.0026, I think it's 5, I'll just round that to 6 for now, coulombs. And I'm going to do the same procedure for C2. So for capacitor 2, to find the charge on it, Q2, I'm going to multiply the capacitance, 130 microfarads, times the voltage, 4.5 volts. This one comes out pretty small because the 130 microfarads is pretty small. So 5.85 times 10 to the minus 4 coulombs, that's 0.000585. So what I wanted to check now, I already checked the voltage. I used the sum of the voltages equals 18 volts to find the voltage. But if I've done this correctly, the sum of the charges, Q2 plus Q3, should equal Q1. And so if you go ahead and check that, I think you'll find that it does come out correctly. And so that's a little bit reassuring that I haven't made any dumb mistakes here. So I hope this example is helpful.